Hello everyone, I'm Rob Carter, one of the IME 156 lab instructors, and I also teach the lecture. So today I wanted to talk about the Eagle circuit board design software that we have an assignment on in the lab beginning in week 1. So I've placed the assignment on the week 1 module. It's the second module following the introductory syllabus, intro, safety module in the beginning. To the end right here is where you can find it, and at the bottom. So this is where we would be beginning the Eagle, which is really an assignment that's based on instructions from a tutorial that is really best assigned as homework. Of course, you can ask questions in lab during my student hours, or you can always reach out to me and we can do a quick Zoom. This works really well. It's a software tutorial, and so as you're working with the software, we can share screen on Zoom, and it works really well, and we can work through any little challenges that you have. So don't hesitate to ask for help. But what I want to do today is talk with you just briefly about what the heck is this tutorial about, what is this Eagle software supposed to do, and why is it important to you. So if we click on that, it'll take us to a brief paragraph here with a few statements and some links to the rest of the assignment. First of all, to use Eagle software, you will have to register with the Autodesk company. Autodesk provides all of their software to students for free. Once you register with your .edu email, I will recognize you as a student, and you'll have access to a number of different software platforms, including Eagle. Now, we have created a tutorial in an Eagle version that is 9.1.0, so we ask you to click on that link and it'll take you to downloading that version, which is a couple of years old. It works great for our application. However, the tutorial screenshots fit best with this version, so you'll want to stick with that version, even though there are some newer releases. It works great. What I want to do is go through the slide deck with you, and you can take a look at that later if you wish, and then that will head us into the final step, which is basically clicking on and downloading these instructions for the step-by-step guide that will walk you through the entire Eagle experience. And the benefit of this will be that you will understand and have working hands-on experience with using a modern circuit design software for making printed circuit boards. Now, this supports and complements what we'll be discussing in week 2 in the lecture, so I'm hoping that you'll get started right away to be able to connect more with the lecture materials. And so, introduction to computer-aided design. There's a layout of a circuit board. This is one that would have components on it, and would basically, this is the a little backbone that you would find in virtually every single electronic device that's ever been made. So how do we make these? How do we design these? Well, there's a set of instructions that come from an engineering design perspective from what do we want to do, and like every engineering design and manufacturing endeavor, it starts with a concept. So, but what is a printed circuit board? So this is a printed circuit board. It provides a platform to which you will attach, assemble components, and then the electrical interconnections between all of the points of contact in the electrical design are determined and designed into the circuit board, and then it is manufactured according to that design. So this software is going to basically provide us with the knowledge and experience with working with the tool to make a printed circuit board. An electrical engineer works with industrial, manufacturing, biomedical, mechanical, other engineering disciplines, because their expertise is in how do you put together the electrical components and assemble them in such a way as to do tasks that we would like to have accomplished. So let's take an example. Let's say that we have a final product here of a continuity tester. It has 2 probes and a switch and a red LED. It's powered by a 9-volt battery, and this device, once turned on, if you probe and touch 2 different electrical points anywhere in a circuit, if those 2 points are electrically connected, the LED light will illuminate. So here is the circuit board inside of this device. Here is the plastic chassis for making it easy to hold in your hand while using, and the two probes. Well, how does this electrical circuit get designed and manufactured? That is what we're going to use as our simple example that could be scaled up to a much more complex electrical system, but we'll start with the basics. We start with an electrical circuit design. We will walk through creating the schematic, the electrical schematic, which is a series of electrical symbols representing the actual components such as resistors and switches and LEDs, etc. You will lay those out on a circuit board layout, which is basically the two-dimensional CAD illustration that represents the locations of all the holes and electrical connection features that will need to be manufactured onto the board. And then that can be manufactured by a printed circuit board manufacturing facility or company, or you could even do it at home if you had the materials. So how do we make this all work? Let's jump ahead. So we're going to take an electrical schematic that we've worked up with the help of an electrical engineer. In this case, you'll be provided, and you will create your own unique circuit design layout, which could be then packaged as a digital file that would be uploaded or communicated to a printed circuit board manufacturer to be built. So we'll create the schematic, the layout, and then we will combine those files and send them to a manufacturer, which you will do. So we start with a footprint editor. The footprint, remember, a footprint is the space, or the imagine if you place this resistor down on this board and it had ink on it and it left a mark. The mark would be this size, representing the footprint, the actual area of the board space that needs to be designated for each resistor on your board that is required. So this is represented by an electrical symbol, as we said, and then here's the footprint. So we need to have all these three pieces of information in order to make a realistic design. Now I want to point out that we will be using various units, including those in the English or imperial system and those in the metric system. And remember that a mil is 1,000th of an inch, whereas a millimeter was 1,000th of a meter, and the conversion rate is such that 1 mil is a very small compared to a millimeter. That is, it's almost 40 mils, thousandths of an inch per meter. And remember that an inch is about 1/40th of a meter, and so that should scale for you. But remember the units. Be careful, be mindful of your units, and we should, as engineers, be able to communicate in both English and metric fluently. The footprint editor, basically a footprint, remember we have a through-hole pad. This is a small pad that's on a circuit board. It has a hole in the middle of it for a lead to pass through for soldering a component, attaching an electrical and mechanical connection to a board from a component. It is done through through-hole pads in certain cases, and in surface mount component cases, which we'll talk about later in the lecture, we have a surface pad, no hole, but just a pad where the component will sit atop the board and be soldered on in a different way that we'll talk about. But each have a footprint, whether it be a pad for the surface mount components or holes for through-hole mounted components. Each are represented, and they must be captured by the software and be able to be communicated through the software design. And so device editor, we will need to make sure that we have the allowance for the two sides of a component to go into the correct locations on the board. So there may be a designation for a pad number, a 1 or a 2, that must be aligned. Pin names will need to be designated and identified in the software too, so we'll be mindful of pin names. Schematic capture, basically this means that you'll be given a schematic design and you will capture it in the digital space using the schematic development tool as part of Eagle. A little bit more about what a schematic shows and includes are important information that are designations that will be interpreted and communicated between engineers to create a design and a manufactured product correctly and to specification. So the reference designators are shortened number letter names for components. In the instance of a Resistor R1 is the first resistor that was introduced into the electrical schematic, and R2 is the second, R3 is the third, R4, and so on. So those are just shorthand names for resistors in this case. The shorthand name for an integrated circuit is the letter U, and so the one integrated circuit in this component has a U1 designation. So those are 2 bits of information. And then the component values. The component value, or the value that a component has in the case of a resistor, for example, is a resistance in ohms, units of ohms. So here R1 is designated as a 2K or 2000 ohm resistor. R2 is a 10,000 ohm or 10K resistor, and so on. So those are 2 bits of information that must be visible on the schematic so that somebody who was going to seek the parts that were required to build this device would know exactly what kind of parts to obtain. Now, not all components have a value. In the case of an integrated circuit is a silicon chip that is also a device or a component, and it has a specification that describes the way that it works. In this case, it's 8-pin component, so it has 8 little electrical connections to the board. That is all contained, all the information describing how those 8 pins function is described by an electrical specification for an LM311M component. So the designation that gets communicated on the board in the case of an integrated circuit is a part number. And so you may find electrical values or you may find part numbers, but each component needs to be identified with some kind of information that describes it so that other engineers can understand what to do with it. And then we have to make the translation from the schematic to the layout. Now remember, the electrical schematic is a series of symbols that represent the way that an electrical circuit will be connected. And now we can actually create, and you will create, your own electrical layout. That means that these components will be moved around by you physically in the digital space to different locations so that they fit nicely around on the specified amount of room that we have for our circuit board. In this case, it has to be a very small circuit board because it has to fit into one handheld continuity tester device. So once you start moving components onto the board, again following the steps in the tutorial, you will see this start to come alive. In our layout, because the layout now represents the actual electrical connections that will carry signal and power between components while this device is in operation, we want to realize that electrical energy moves through traces in either efficient or not very efficient manners, and our goal will be to create this pathway in efficient manner, so we won't want to have a lot of sharp turns or jogs up and down and around, but rather we would rather have rather straight connections between components as are shown here. We don't want to have any 90-degree bends. If you imagine a moving alternating signal moving down this line and it runs into this right angle, part of that signal will reflect back and some of the energy will be lost. Whereas if we have an obtuse angle, we would be able to have that most of that energy of that signal not lost in the reflecting back, but rather continuing forward on its path towards its destination. So a couple of rules about proper, efficient electrical design will have to follow for highest success. In this case, remember, no 90-degree angles, no necessary bends. We want to be efficient, and we can keep our angles to 45-degree increments. Not exactly automatically done by Eagle, but very easily accomplished by Eagle. When you grab the node, the corner of your circuit trace, and left click and hold it and pull it down, it will automatically change into a 45 for you. So very easily done in Eagle so that you can follow that design rule and make a very efficient design. So here we have an example of our layout. There are a few constraints. These are the large pads that are created for the connection of the 9-volt battery, which sits in a compartment over off to the side in the device. Over here on the opposite end are 2 large pads for a large area of connection for strength to the board, and there will be 2 leads for the positive and negative probe leads for the device to be connected on the other end of the board for efficient sort of layout of things. We have our integrated circuit, we have resistors, we have full freedom of where to put what, where you would like, within some constraints, but you get to be creative with where you lay out your components in your board for efficiency. And as you can see, there are mostly non-90 degree angle bends on this board. Maybe you can spot a non-90 degree angle board that should be changed into 245 somewhere. This one right here next to the R5 reference designator you might have picked up. So if you caught that, good eye. Reference designators cannot overlap. Reference designators are D1, R2, and so on. Those need to be visible. Those are to instruct the manufacturing person what component to put in this location. And also, if rework is required, which components need to be moved around or replaced. And when you're testing, you can reference the information that is associated with the D1, in this case a diode. It needs to be visible. So in other words, this will go along for the ride with your component, these reference designators. However, they will not be necessarily located in a location that makes sense. You will need to grab and move the reference designators around using your mouse. In this case, as you notice, all of the reference designators are visible once the components are installed. So if this integrated circuit's installed, this chip's installed here, you can still off to the side read the reference designator. One of the most common errors in communication of their design that students make early in the Eagle learning process is to neglect to place the reference designators in readable, legible locations where they won't be covered by a component. So be mindful of your reference designators because they need to be communicated clearly. You have a couple of mounting poles to include, very easily done in the digital space. You will need to supply, your Eagle design will be completed and you will need to upload your design package to Canvas. Any questions about the Eagle experience, I'm happy to help you. Again, reach out and we can get together in lab, we can get together in my student hours, or we can get together a meeting in Zoom. Thank you for your attention.